Hello guys, the time is now 12:01 p.m. Central Time. I am your host, Dr. Matthew Richardson, and this is another stream of CosmoQuest Astro Office Hours. Um, excuse me. Give me a quick moment to quickly verify that I'm streaming. So I'm going to do my usual, which requires me to open up a Chrome browser and navigate over to Twitch. All right. And so we are live. Oh, this is a first. I can actually access the chat immediately. All right, this is making things really easy. Go really easy today. So, all right. So a quick hello to the chat. Let's see who's all here. Hello, Peter, and hello to Tchaikovsky. But for all others who are also here, welcome. Okay, this is just a quick warning, but it looks like my connection is again starting to do some weird stuff. Hopefully, it does not continue to do this. Are you guys able to hear and see me just fine? Okay. The connection looks like it's holding at a steady green. All right, let's just go ahead and get into the problem for today, which is actually just a continuation of what we were talking about in the previous stream. So, to kind of recap what we've already went over, the idea was to be able to derive um, Newton's law of gravity from general relativity. And so the problem that we set up was what is the Newtonian gravitational potential at a distance r due to a particle at rest in space according to general relativity? And so this was actually my attempt to respond to another question that was asked by Larry, in which he wanted to know, does Newton's law of gravity apply when one or both of the bodies are moving relativistically? And of course, the short answer to that is no. And to really give a thorough answer to that question, that is, give some sort of quantitative response, you'd have to do a lot of stuff. And we're kind of doing that stuff, but with a simpler problem. All right, so E equals mc squared. That's Einstein's famous formula. All right, so the conditions that we are implying to this problem is that the particles must be moving slowly. In our case, our particle is just at rest. The region that we're analyzing must have a weak gravitational field, of course, due to the particle, and that field cannot be changing in time. And so I introduced in the previous stream this equation that we're seeing here, which is Einstein's field equations. And so basically it relates, if we were to ignore the g sub mu nu, and look strictly at the middle term or the middle equation portion of the equation and the far right hand side of the equation, it basically relates the curvature of space-time to properties that are intrinsic of the mass within the region that we're analyzing. All right. Yeah, the more complicated answer is what we're looking at right now here, Peter. This equation right here will actually answer Larry's question. But it's the breakdown of this equation that's the tricky part. And so we end up going into what all these various terms mean in the previous stream. And to kind of summarize that, T sub mu nu is our stress energy tensor, which is a 4x4 matrix, which basically yields all the information that's intrinsic to the mass within our system. And so we end up discovering that given the problem that we have, that particular 4x4 tensor matrix, which can be put in terms like this, reduces to only having a single element that's non-zero. And that's the T sub 00 element, which basically is going to be the mass density of our system. And so that pretty much handled the right-hand side of the equation, which was pretty simple. The left-hand side of the equation, that is the part of the equation that deals with the curvature of space-time and stuff like that, it's a little more complicated. But luckily, we only have to worry about one component of that of the tensor that's associated with the left-hand side of the equation. And that's, again, the 00 element, but it's the G sub 00 element. And so we were in the process of going ahead and trying to solve for that. All right. And so since our previous stream, I have made a few modifications. I've added some stuff, but I've also made a few modifications that I realized that I left out in the previous stream, which I'll get to in just a second. So the very first thing we needed to do was be able to establish what our metric tensor would be. And so the idea here is, and I'm going to try my best to explain this using the typical analogy that's given for space-time, and that is if you have a flat, let's say a flat, what is it, sheet, a flat sheet, bed sheet, if you will. With this flat sheet, that can be defined by some metric or metric space. In this situation, the best way to be able to define that space, that is, the best way to be able to define the distance between 2 points on that space, you can use what's known as a Minkowski metric, which in this situation would be represented by this term eta sub mu nu. But the moment we start placing mass on our flat bed sheet, you'll start getting these little dips within the bed sheet, right? Wherever the masses are being placed. The heavier the mass, the more the dip will be. Well, those dips in our sheet can be thought of as small perturbations in our flat space-time, right? And so, to be able to define the distance between 2 points, given this flat space-time that can have dips in it, we can be able to use the equation that we've established here. where we have G sub mu nu is equal to eta sub mu nu plus those little small perturbations or those small dips in our sheet due to this term h sub nu mu nu. Where in this case we're considering only these small perturbations to be much less than the value of 1 in our situation. So the one thing that I added was the fact that h sub mu nu should be much less than 1. And I've also added what the metric would basically look like. Where where this metric is basically just a diagonal matrix. So all the elements, all the diagonal elements are equal to 0, and we're only concerned with elements along the diagonal. Yes, Guido is probably cooking right now. It's dinner time for him. Lunchtime for me, which I cannot wait to get to actually. But I'll think about lunch later. Right now I'm thinking about general relativity. And so this is going to end up being the metric that we end up getting. Now note that all we've done is taken the matrix eta sub mu nu, which I'm going to scroll down. And as you can see, there's a bunch of like math in here now, which was not here in the previous stream. But basically, this is going to be our Minkowski metric tensor, which is basically for a flat space-time. And all we've done is taken this metric tensor, which I should note that this is going to be in Cartesian coordinates. I guess this is going to be in Cartesian coordinates, where the 0, 0 term corresponds to our temporal coordinate. The 1, 1 term corresponds to our x coordinate, 2, 2 term to our y, the 3, 3 term to our z coordinate. But we've basically taken this matrix or this metric, and we've slightly modified it by adding on the elements that you'd get for your small perturbations. Let's scroll back up. There we go. All right. So this is basically what the metric would be that we're going to end up working with. Now, in the previous stream, I also mentioned that there was this thing called contravariant versus the covariant vector or matrix. In this situation, the matrix that I'm showing is the covariant matrix. But for our problem, we're also going to need access to the contravariant matrix, which you can do by using a special relationship. In this case, our contravariant matrix for our metric will be given by this matrix. All right. And so, moving on from there, we're able to now begin to actually start to work the left-hand side of the equation now that we've defined what our contravariant and covariant metrics are for the problem. And so we basically need to solve what's known as the Ricci curvature tensor. And so I'm not covering everything that I said in the previous stream because it's a lot of information. I'm just hoping that you guys are probably here, but if you weren't, by all means, ask questions, and then I'll explain it. But I'm just basically giving a recap of what we went through in the previous stream. And so we end up getting to this, the Ricci curvature tensor, which is going to allow us to be able to calculate curvature in our space-time. So I believe, well, yeah, this is going to be the general form of the equation we're working with. I've already went ahead and substituted in what the indices are for our Ricci curvature tensor. So we're only going to be concerned, with, of course, with the 0, 0 term. And again, the reason why we're only concerned with this term is because of the fact that our stress energy tensor only has a non-zero element for that particular term, the 0, 0 term. If you scroll back up a little bit more, given this equation, if only T sub mu nu, or the T00 term, is defined, well, only the R sub 00 term could be defined, as well as in this case, we'd only be concerned with this particular equation, that is, with the G sub 00 term, with this equation. In general, no, we'd be concerned with the entire metric, but for the purposes of this equation, we're only concerned with the G sub 00 term. But as you'll see, as we work through the problem, all elements along the diagonal are going to be important. All right, and I hope that made sense. All right, so the one thing that we also noted was that given the fact that the field is static, all time derivatives will be equal to 0. And I'm going to explain the reason why that's the situation and why there's time derivatives in the first place. But let's continue from there, though. So I've actually filled in some more information. So we're going to break down, essentially we're going to break down every single term, right? So given this equation, starting on the right-hand side with the first term, that is the gamma or the delta or the partial derivative with respect to rho of gamma superscript rho sub 0, 0. So in the previous stream, I also mentioned that whenever you have an index that repeats itself and it's only present on one side of the equation, then you're summing over that index. And so that first term ends up expanding, and I don't want to show all that. Hey, Adam. And hello, our Astro. Welcome, guys. And hello, Uncle Bill Druin. And so that first term actually expands. And it expands out, and I'll actually scroll down, but I need to explain where some of this math comes from. And so that first term actually expands out to being 3 terms. Well, actually, it's 4 terms, but we can ignore the very first term. So what I'm going to do is, because I was working through the math and I left some stuff out on purpose and for good reason, but I'm gonna add it back in though, so it's clear what's going on here. Zero. I think that's it. Yeah, I think that should be. For more than one reason, this might be actually just not existent. All right. So I've modified the first equation for term 1 so that it shows all the terms that will be all the components that will be present on the right-hand side of the equation. And so this should be a partial with respect to the 0 coordinate, which in this case is our time coordinate, with a gamma superscript 0 subscript 0, 0. But the issue with that term is that, remember what we stated earlier, all partial derivatives with respect to the 0th coordinate or the time coordinate are going to end up equaling 0 anyway, independent of whatever the value you get for gamma. So that particular term goes away and we don't have to worry about it. Did I repeat that actually? All right, perfect. All right, so that equation just reduces to being the last 3 terms on the right-hand side of the equation. And then you start getting what you're seeing below, but I need to explain some other stuff before we get to that. So I also mentioned in the previous stream about these Christoffel symbols and their importance in being able to solve this problem. It turns out that there's a lot of them. There's a lot of these Christoffel symbols for the problem, and really, that's probably like the more difficult part of it all, just being able to make sure you calculate them all and keep track of them. And so, I mean, there's ways around this. You can use summation notation and be able to not have to worry too much about calculating them all and knowing what certain terms cancel out. But for the purposes of this problem, I went ahead and I calculated them all. It's not too difficult. So I'm going to scroll down. And so I also have here the solutions for all the Christoffel symbols. And we'll just work through like a couple of them, and then you'll hopefully you'll get the point of how to go about solving them. So the very first thing we need to realize is that it might be actually useful if I open up another window so that you guys can see this. Just give me one quick second. So let's see. That's open. Let's go ahead and switch scenes. There we go. So what we're gonna do is we're gonna go to hopefully Google should not Google but Wiki should have what we're looking for. And so the Christoffel symbols that we're going to be working with for this problem are the Christoffel symbols that are of the second kind. So there's a first kind and there's a second kind. And the ones we're working with are the second kind. And the equation that's the most relevant for what we're doing is this equation here, where I probably should also note now, because I probably didn't note it earlier in this stream. In my previous stream I did. But each of the partial derivatives, whenever you see a partial in a subscript, like subscript 0, it would be the same thing as almost as saying, given the equation we have in front of us, the same thing as saying a partial with respect to, so partial over partial x, and then it'll be a superscript 0 next to the x. I might end up having to explain that again, probably, because I feel like that was probably not exactly a good way of explaining that. But this is the equation we're dealing with for our Christoffel symbols. So I'm going to quickly go back. Before I do that, let me check the Christoffel symbols puke. Yes, I agree with you. Hey, Susie. I definitely do not miss doing these problems. These particular problems I do not miss doing. All right. So let's go back here. And so what you basically have to do is find all the combinations, actually. Well, yeah. I'll go back here. You have to find all the combinations. And we're just looking at this equation and noting that the left-hand side of the equation is gamma, our Christoffel symbol, with the indices I, K, and L. You basically have to find all combinations for I, K, and L for these Christoffel symbols. So there will be a gamma superscript 0 subscript 0 a gamma superscript 0 subscript 1 0. You'd have to find all these combinations and solve for all of them. But once you learn the little trick, you'll know exactly which Christoffel symbols um, are trivial, which basically are equal to 0, and which Christoffel symbols actually give you a non-zero value. So going back to here, let's go ahead and explain what I mean by that. So the Christoffel symbol I'm solving for here is going to be for the 0, superscript 0, subscript 0, 0 Christoffel symbol. And so it breaks down to having 4 terms, because remember, we're going to end up having a sum over an index. In this case, and again, I have to go back to my previous. In this case, we're using this exact definition. And given that on the right-hand side of this equation, we have m being a repeating index and not being present on the left-hand side of the equation, we're summing over m. And so you have to find all the for a given IKL set, you're basically going to be summing over all values of m. And in this case, we only have 4 coordinates, 1 temporal coordinate and then 3 spatial coordinates. So m basically sums over those 4 coordinates, which we've defined as 0, 1, 2, and 3. So I'm going to go back. So flip-flopping back and forth here. I'm going to go back, and essentially what we're going to end up doing is getting four terms, which are the terms we see here, where I've basically just inserted in the values for what m would be for those 4 different terms. And as you can note with this particular Christoffel symbol, it equals 0. And the reason why it equals 0 is because, well, 1, if you look at many of the terms in here, many of them have partial derivatives. Where the all of them have partial derivatives, but the partial derivatives in which we are taking the derivative with respect to the 0th coordinate or the time coordinate, those automatically are going to be equal to 0. So a lot of the terms disappear simply because of that. But not only because of that, if you notice, for every single term, we have a g superscript 00, a g superscript 01, g superscript 02, g superscript 03. This is basically our metric, our contravariant metric that we've defined already. And so if we quickly look at that, we'll notice something interesting about it. So I'm going to scroll back up. This is a lot of scrolling here. The key thing I want us to note is that only the diagonal elements are non-zero. So if you ever get, for example, if you ever get G10, right? Well, G10 is equal to 0. So anything multiplied times the G10 element is going to be equal to 0. So you can actually ignore any sort of term that has an off-diagonal element of the contravariant metric that we're using here. All right. So going back down, oh God, this is a lot of scrolling. All right, here we go. So we're back. So basically, we can ignore the last 3 terms, the ones that have G01, G superscript 01, G superscript 02, G superscript 03. However, the G superscript 00 did have a non-zero element. So now we need to evaluate what's going on inside of the parentheses for that particular term. And again, if you notice, all of the partial derivatives are with respect to the 0th coordinate, which we know is equal to 0. So for this term, it's equal to 0 in total. But if we move on to the second term that I've defined here, the gamma superscript 0 subscript 1 0 term, and noting the fact that if you basically switch the values of the indices in the subscript, it's the same thing. We notice that again, we're not even going to concern ourselves with any sort of term that has an off-diagonal contravariant metric element. So none of those terms are showing up here. I've completely just left them out, and I'm focusing strictly on the g superscript 00 term and looking at its partial derivatives. Well, I'm looking in there, and I see automatically that, hey, two of those partial derivatives are with respect to the zeroth coordinate. I can ignore those automatically, and I'm left with just the partial derivative of the first coordinate, or the first coordinate of g00. Well, I can actually evaluate all this information. So earlier I stated that, let's go ahead and just break down this equation here. And I'm talking about the middle equation on the screen. The 1/2 times g sub superscript 00 times the partial with respect to the first coordinate um, of g sub 00. So if we focus in on the g superscript 00 term, and we scroll back up top, again, another scroll. I apologize, guys. It's a lot of scrolling. And we focus on that term, which is given here. That term corresponds to -1 minus h superscript 00. Well, it just so happens to be that h superscript 00, like its counterpart, h subscript 00, both of those values are much, much less than 1. And because of that, whenever you see whenever you actually think about these diagonal elements, they basically just result back to just being simply, in this case, you can round it off to the point where it's just going to equal -1. Because of the fact that the amount that you subtract from -1 using the h superscript 00 value, it's not going to be much anyway. So, going back to our Christoffel symbol for that term, g superscript 00 is equal to -1, which I've accounted for in the third equation I'm showing here by just putting a negative sign. But one more thing to note is that we're taking a partial derivative. So it actually might be best if I write this stuff in just so that it can be clear what's going on here. See if I can find it. Here, it's right here. So I'm actually just going to write that in. So this simply just becomes -1. So I'm going to put a -1 there. All right. So g00 just simply becomes -1. And your partial, though, with respect to the g sub 00 term, becomes this. So where are you? Right here. Let's put a parentheses around it. And this should end up becoming 1, and it's the covariant one, so 1 plus h sub 00. And so really all I'm doing is I'm substituting in what those values are. And whenever you take the partial derivative of a constant, it's equal to 0. So the partial derivative of 1 with respect to anything whatever coordinate you're doing it with respect to is going to equal 0 anyway. And so all you're left with, the only thing remaining is the partial derivative with respect to whatever h sub 0, 0 may be, which we haven't defined yet. It's the general variable for now. And so that's basically how you go about solving these Christoffel symbols. And as you move on, though, you'll begin to see that many of them are going to end up equaling 0 anyway. And so that's exactly what I've done here. I've went through them, and after a while, you kind of get into like if you begin to understand them fairly well, you can actually use a little trick, which I'm not going to try to explain, but you can use a little trick to determine exactly which terms are going to be 0. Let me quickly check comments because I'm pretty sure I've missed a lot of comments here. Let's see. No, I have not missed a lot of comments. That's good. Okay, I'm not seeing many comments. So either that means you guys are understanding me, or it's like, Matt, what are you talking about right now? Hopefully it's the former and not the latter. Okay. Well, let me continue. So I've solved for all the Christoffel symbols. I can't remember exactly how many there are. Quite a few. I guess I could do the math and figure it out, but all the combinations, but I'm not going to worry about it too much. Okay. So going back up top, we were basically defining what each term is going to end up being. And so each term for our Ricci curvature tensor is going to be, or the 0, 0th element of the Ricci curvature tensor. And so for your first term, breaking that down, you end up basically just getting that the tensor breaks down to being this negative 1/2 times the second order partial differential equation of h sub 0, 0. Which, if I'm not mistaken, I mean, now that I'm looking at this, this is basically just, it looks like it's Laplacian. Much of all this stuff I've done, guys, was this morning, so some of this stuff is going to be kind of a revelation to me as well. So yeah, I think this is the Laplacian. It's like negative 1/2 of I think that's del of h sub 0, 0. All right, so that's what we end up getting for our very first term in our Ricci curvature tensor. For the second term, and again, guys, remember I stated earlier that, and I even stated here that all terms that involve partial derivatives with respect to the 0th term are equal to 0. And as you can see, though, the second term in our Ricci curvature tensor is solely dependent on partial derivatives that are with respect to the 0th element or coordinate. So that term goes to 0 automatically. So we can ignore that term as well. Now moving on to the third term. Now this is the third term up here, right? This gamma superscript rho subscript rho lambda times gamma superscript lambda subscript 0, 0. Well, it's two indices that you're repeating over, or they repeat two indices that repeat themselves that you must sum over. So you end up getting, and I think I did this right. You end up getting 16 terms from out of this. And so, given that I've defined all of my my gamma values, I can basically just go ahead and plug them right in. And so, I want to make sure that I did this right. So let me kind of like zoom in a little bit so we can see everything. Let's see if my face might be blocking. No, it's not. Perfect. All right. And so basically we're just going to end up substituting in what our gamma values are. And so I've done that here. And this is the part of the math that you just got to make sure you're keeping track of everything. And so I threw these in here and I want to make sure I've just got the math correct. Okay. I think everything's good here. And again, you do this exact same thing with term 4. You can expand it and then go ahead and start plugging in terms and seeing what you get. Hey, skeptic, how are things going? The answer is 42. If only it were that easy. All right. And so to kind of actually recover the answer, the solution for the zeroth term of the Ricci curvature tensor, I'm now starting to put the terms back together. And from the initial equation, we basically subtracted term 4 from term 3. And so now I put that together and I end up getting this. I'm actually quite curious, guys. Is anything what I'm saying making sense? As of right now, it's in a very generic form because we don't exactly know what the elements of our perturbation matrix is at the moment. We're going to assume we just don't know what they are. Well, that's funny. All right. And so now putting everything back together, we end up getting this particular value for the 0th term of our Ricci curvature matrix. Now, this is the reason why. This is the reason why, or part of the reason why, it's difficult to actually answer Larry's question outright. So, with Larry's question, he wanted to be able to know exactly what happens, or can we use Newton's law of gravity for relativistically moving masses? And the thing about it is that you end up starting getting one, these you have these second order partial differential equations, one, but two, you end up having terms of the Ricci curvature matrix that are not simply just R sub 0, 0. You also have to solve for other elements within the within that matrix, because of the fact that your stress energy tensor is now no longer simply just that one element in the corner. So it becomes a lot more difficult, and if I'm not mistaken, you're gonna basically end up getting nonlinear second order partial differential equations to work with. They can't be solved analytically. All right, so basically this is going to be our R sub 0, 0 Ricci curvature tensor element. And so now we can go ahead and we can define then what the scalar curvature is going to be. And again, I'm just basically using the definitions that are given for these particular elements or variables. And we end up getting that the scalar curvature tensor is the scalar curvature is basically equal to negative of the negative of our 0,0th element of our Ricci curvature tensor. And so with all this information, you can actually go ahead and start making an attempt to go ahead and solve for what the left hand side of the equation is going to be, or what our space-time curvature is doing. So just plugging in values, and all I'm doing here is solving for the 0,0th element of our Einstein tensor, which basically is a function of the Ricci curvature tensor and the scalar curvature. And it breaks down like this. Now I want to actually change this here. I want to change this. So again, guys, this was the math I was going through this morning. And so I want to change this actually. So I'm going to erase all of this. Hopefully I can get this to fit. Or I'll leave it like this actually. And I'll go down a different path. Slightly different from what I was planning on doing at first. Okay. And so let's relate this now to the right-hand side of the equation that has the stress energy tensor. So we're essentially going to get let's see, no indent. For our Einstein field equations, is the following. We get that this 1/2 of r sub 0, 0 is going to be equal to, and I'm just going to do a quick copy and paste. Now, of course, you can get this result that I'm about to put on the screen in a few seconds. You can get this without actually even solving for what any of the elements of the Ricci curvature tensor is. And so we end up getting this relationship. And so if I move the 1/2 over, we get 1 this is going to be 16 times pi. And we can also make one more substitution, or we can actually make a few substitutions in actually, but we can also put the fact that 2, we know that the T sub 0, 0 element of the stress energy tensor is equal to rho, the mass density of our system. And 2, we can make a substitution in for r sub 0, 0. And so I'm going to go ahead and do that now. I'll leave it here, actually. And let's go ahead and substitute it in. So that this works out neatly, I'm going to do this. Copy this. Move that there. Better yet. I'm trying to think of the best way of being able to put all this information together. I'm going to switch things around just a little bit so that everything's going to be on the screen. Let's see if this typesets. Okay. Where is it? And so basically what I've done is I've moved the left-hand side of the equation over to the right and the right-hand side of the equation over to the left. I'm looking at this now, and it's starting to look like what I want it to look like, but I'm seeing that there's something that's a little off here. I definitely see the Laplacian, which is what I kind of want. But the coefficient is off. It would need to be 4. All right, let me quickly check something, guys. So the issue that I'm having here, that I'm seeing, is that the very first term I'm seeing there, the negative 1/2 times essentially what would be known as I think it's del. So let me pull up. First, let me look at comments because I want to make sure that. So I'm looking at this, and again, I'm pretty sure it's coming out the way I want it to come out, but the coefficient is kind of throwing me off there. So let me bring up something really quick so I can explain what I mean. So scene. Let's go back to scene 1. I'm going to pull up, and it should be the Laplacian. And so this is the Laplacian, and I think that's the operator called del. I think that's right. So this is the Laplacian, this equation I'm showing here. And so if we go back to what I've derived so far, let's make this a little bit bigger. Hopefully I can zoom in a little bit. This sum that we're seeing here, only I could highlight it. That would be nice. But basically this sum of the second order derivative of h sub 0, 0 plus the second order derivative. Oh wait. That's one thing that's not right there. That should be a 2. Should be a subscript 2 there. So let's fix that. So basically this sum that we're seeing here, ignoring all the other terms and only focusing in on this little part in the parentheses. Partial with respect to 1, the second order partial with respect to 1 of h sub 0, 0 and so forth. That in itself is the Laplacian, which is what we want actually. But the coefficient of that is the negative 1/2. It's kind of what's throwing me off here. It's for all the other terms, they actually all end up going to 0. I will figure this out. What's going on? So let me see. Let me go back. And the answer, if the answer was 42, I'd be so happy because I would just put 42. But I definitely will figure out what's going on. Just give me 1 second, guys. So let me zoom back out. And so this particular term comes from the first element, or the first term in the Ricci curvature tensor. Let's go back up there. Let's see, what did I do with that? So this is term 1. Peter, actually, I'm pretty sure at some point there's like a solution that for this that probably is like 42. And throw some units on that, and like that's the answer under certain conditions. I'm not quite seeing it just yet. Let's see. They all have a factor of 1/2, and they're all negative. 1, 0, 0 times 1. Its derivative g11. So g22, g33. Those will be positive. Okay, so if it's not this term, this is the only term though that would give me a second order partial differential equation. Not gonna lie, guys, I'm actually kind of stumped here. Because as far as I can tell, this is the only term that's going to end up giving me a second order partial differential equation. The other term that could give me that is equal to 0. And these terms are just simply the product between two first order partial differential equations. Okay, it's actually now 1 o'clock. I'm going to definitely come back to this, and I'm nearly done with finishing up this problem actually. So I'm going to figure out what's going on here, and definitely talk about how to solve this problem in our next stream. But guys, I hope that everything I've said so far made some bit of sense. And if you guys have any questions, of course, by all means, just go ahead and send them my way. But nevertheless, guys, thanks for stopping by. I'm going to take a little bit of time out and figure out what's going on with this. And then I will definitely see you guys on Friday with all like the corrections in the correct way forward. All right, guys. Thanks for stopping by. Definitely had some fun talking about this. And I will see you Friday at 12 o'clock p.m. Central Time. All right. Thanks again, guys. Bye.